have defined in terms of convergence of sequences. Further, I also added one more statement, and I said that you can use this particular statement as the definition of definition of continuity, right? So what was that statement? So I have boxed it here. Okay. So what does it mean? What does it says that it says uh, function f is continuous at x in x. This is equivalent to saying that you look at any open set V, okay, look at any open set V containing f of x, okay, look at any open set V containing f of x in Y, okay, so this is happening in Y, this is happening in the range or in the codomain. Now, depending upon this V, if we can find an open set U, okay, if we can find an open set U which contains the element X and such that image of U under F, right, F of U, image of U under F, it sits inside V. Right? If this is true, then we say that the function F is continuous at X. Now look at the statement 2, right? If you look at the statement 2, in the statement 2, the continuity is defined purely in terms of open sets, right? In definition 2, the continuity is defined only in terms of open sets. And you people have known that topology, right? If you go back to the definition of the topology, then topology, it's been defined in terms of open sets. So the statement 2, it facilitates us to extend the definition of continuity from metric spaces to topological spaces. Okay, so this is the significance of definition 2. If you wonder what is the significance of definition 2, then definition 2, it facilitates us to extend the definition of continuity from metric spaces to topological spaces. Okay, so that's why this second statement, okay, this second statement or this characterization of continuity, this is characterization of continuity, okay, is very, very important. It's very, very important. I should have added it somewhere, uh, but I'm afraid that I can we add blank lines here in OneNote. I just wanted to add this significance of this second definition. I don't think so that will happen. Okay. So we can do one thing. Okay, this is risky. I just don't want to lose this. Okay, so yeah, now let's do a few examples. Okay, so I have solved these examples while practicing my writing on this board. So here uh, we are given two metric spaces. Okay, we are given two metric spaces x and y. Okay, so x and y are two metric spaces. Further, there is a function f from x to y. Okay, function f from x to y, and this function is continuous on x if and only if, okay, if and only if for every open set V in Y, if and only if for every open set V in Y, the inverse image, okay, the inverse image of F, the inverse image of V is open in X, right? So let X and Y be metric spaces, okay, let X and Y be metric spaces, or they are just topological spaces. Further, we have a function f from x to y. This function is continuous if and only if for, this is very important, okay, for every open set, for every open set V in Y, its inverse image F inverse of V is open in X. Right? So this is also one characterization, one equivalent definition of continuity. Okay, one equivalent definition of continuity. Now is the statement clear? Do I need to break it down? There is nothing to break down. Okay, so this is the fair and if statement. So first, assume that f from x to y is continuous. So let f from x to y be continuous and v, which is a subset of y, is open. What do we want? We want to show, this is our objective, we want to show that f inverse of x is open. F inverse of x is open. Now let's start. Let's start to prove that if inverse, this is not x, f inverse of v, okay? This is the f inverse of v. F inverse of v is open. So now take any point x in f inverse of v. Okay, take any point x in f inverse of v. So this implies f of x belongs to v. Okay, this implies f of x belongs to v. Now since v is open, right? We have assumed here. You can see we have assumed that v is open. So since v is open, there exists an open set. Right? Since V is open, there exists an open set Ux such that this X is contained in Ux and F of Ux is contained in V. What is, from which we derive this statement? Why this statement is true? Why this statement is true? Rutuja.
Sir, from this above theorem.
Okay. Why this is true? Because we are given that this function f is continuous. So it means this statement true, right? This statement true holds for f. And what is happening here? So there is open set V, right? V is open in Y, right? And since f is continuous, we get an open set Ux, right? So guarantee of this open set Ux is given by statement 2, right? And what type of open set this Ux is? This Ux contains an element x, right? Here you can see Ux contains x. So this open set contains x, and further the image of Ux under F is contained in V, right? You can see it here. Right? So this statement is guaranteed by the statement 2 discussed above, right? Okay. So what does that mean? That means Ux, right? F of Ux is contained in V. That implies Ux is a subset of F inverse of V, right? We are just taking the inverse on both the sides. Ux is a subset of F inverse of V, right? Now what has happened here? Can somebody tell me what has happened here? So we have fixed a point X, right? So from this fixed point X, we found an open set Ux such that X is contained in Ux, and further this Ux is contained in F inverse of V. What does that mean? So this is the next is something extra statement. So that means this F inverse of V, we can write down this F inverse of V is equal to union of these sets U sub x where x belongs to F inverse of V. Now each Ux is open set. Each Ux is open set, and this is arbitrary union of open set. So we know that arbitrary union of open set is open. Therefore, F inverse of V is open. F inverse of V is open. Okay. If you have any question, please ask me. Sania,
Yes, sir.
काय प्रश्न है?
No, sir.
गुंजन, ऋषि,
Yes, sir.
question,
No, sir.
Varda,
No question.
okay, Ankita.
No, sir.
Now, conversely, assume that. Assume that. Seems like conversely, conversely assume that. Conversely assume that for every open set, okay, you take any open set V in Y, F inverse of V is open in X. Conversely assume that for every open set V in Y, its inverse image is open in X. What do you want to prove? We want to prove that this function F from X to Y is a continuous function. Now again, we are going to make use of the second statement. Okay, we are going to make use of the second statement over here. So this one. So everybody please read the second statement. So given an open set V containing f of x in Y, we can find an open set U containing x such that f of U is contained in V implies the function is continuous at x. Right? So we are going to make use of this second criterion again. Okay. So take any arbitrary point x and let V be an open set. Let V be an open set such that f of x is contained in V. Right? Now define U to be F inverse of V. Okay, define U to be F inverse of V. By our assumption, okay, by our assumption, F inverse of V is open. So therefore, this set U is open in X containing X. Okay, it contains X. Why it contains X? Because your element X, right, is such that f of x is in V, right? So that is equivalent to saying x belongs to f inverse of V, right? So therefore, this U, which is f inverse of V, is open in X by our hypothesis, and it contains X. Further, if we take the f of U, or if you look at the image of U under F, then this image sits inside V. And therefore, by the statement which we discussed in the beginning, by that statement, F is continuous at X. By that statement, F is continuous at X. And X was any arbitrary point. X was any arbitrary point. Therefore, we conclude F is continuous on X, right? Okay. Take your time, and if you have any question, please ask me. Vinci.
Yes.
I will draw the pictures. Okay, yesterday I do remember drawing the pictures. When a function f is continuous, so suppose we have two metric spaces. Okay, we have two metric spaces. So this is our first metric space. Let's say x. This is our second metric space. Let's say y. When and there is some function f. Okay, there is some function f. Now, when is this function is continuous at a point x? Okay, or in a more general setup. Okay, let's just not discuss continuity at a point. When this function f is continuous, right? So you take any open set. You take any open set here. Call this V and look at its inverse image. Okay, so look at its inverse image. So this is your F inverse of V. If F inverse of V is also open in X, then our function is continuous. Then our function is continuous. Right? Or if you want to discuss statement 2 in pictures, what does it mean? That given an open set V containing f of x in y, we can find an open set U containing x such that f of u is equal to V. What does it mean? So here in the statement second one, we are discussing the continuity of the function at a point. Okay, so what does it mean? You fix any point. You fix any point x here. Okay, let me take some different color. It's not working. Fix any point x here. Okay, now f of x is somewhere here. Okay, now take any open set. You have all the choice for this open set V containing f of x. Okay, so you have all the choice for this open set V containing f of x. Okay, I will draw a big. So this is your open set V, which contains f of x. Now, depending upon this open set V, if I can find here, okay, I can find here an open set U such that the f of U, okay, it's contained in V. So this is your f of U, and this is your U. Okay, U over here is open. Okay, U is open. So U is open. V is also open. This is what your definition says. Okay. Just understand the chronology. What thing we fix, which things we have control over, which things depends upon the right. So for example, we can fix our x. We have control over v. Depending upon this v, we get u, means the u depends on v. Like that. So if you ask me, this v is playing the role of epsilon, and this u is playing the role of delta, like that. Okay. Any question? Just take it. Okay. So this is another criterion for continuity. Okay, this one is another criterion for continuity. Now just so the proofs are a little smart, but they are not difficult at all. Okay, they are not difficult at all. Proofs are not difficult. Okay, now let's prove one more result. So here again, again we are given two matrix spaces or two spaces. These spaces can be topological as well. Okay, not necessarily matrix spaces. That's why I have put this metric in parentheses. Okay, so let x and y be two spaces. It could be matrix spaces. It could be topological spaces. Show that the map f from x to y is continuous if and only if for every closed set B in Y, okay, for every closed set B in Y, its inverse image F inverse of B is closed in X. It's closed in X. Now compare this statement with the statement which we have just proved. Compare with this one. Compare with this statement. So here, what is happening is the inverse image of an open set, right? Under a continuous map, inverse image of an open set is again open, right? And what is happening here is under a continuous map, inverse image of a closed set is again closed. It is again closed. Okay. Please read the statement. Now, who will like to help me to prove this one? The hint is given there. So set V is equal to complement of B in Y. So what does this implies? B is closed. What does this implies? This implies V is
Open.
open in Y. Now further, we are given that function f is continuous, right? So since f is continuous, f is continuous by the earlier exercise, what we can conclude? F inverse of V is, by the earlier exercise, what is the pre-image of an open set? F inverse of V is open, okay, in X. F inverse of V is open in X. That is, F inverse of complement of B in Y is open in X. So this is same as saying, I'm making use of some set theory. This is same as saying F inverse of B. So what does this mean? Is F inverse of Y minus B is open in X. This is same as saying
Sir, F inverse of Y complement B would be closed in X, no?
yeah, in X. It is in X. Right. So what is the inverse image of complement of B? So this is nothing but look at the inverse image of B. Look at the inverse image of B in X and take its complement. So X minus F inverse of B is open in X. This is open in X. So this implies F inverse of B is closed in X. It's closed in X. Okay, so I have borrowed one result from the set theory. Okay, I will just mention the result which I have borrowed. It says that if we look at inverse image of complement of B in Y, this is same as look at the inverse image of B and take its complement in X. So this is a set theory result. You can prove this one. Okay. So what does that implies? That implies F inverse of B is closed in X. Right? So we started our argument from B being closed in Y, and we concluded that F inverse of B is closed in X. Yeah. I will just show you the whole argument. So let me add the hypothesis here. Otherwise it will find a little difficult. So what is our hypothesis here? Can somebody tell me which part am I proving here? Direct part or converse part? Which part we have just proved? Direct part or the converse part?
Direct.
Direct part, right? So what we have assumed? We have assumed F to be continuous. Assume F from X to Y is continuous. That is what we have assumed. And B is closed set. This is what we have assumed. What was our objective? Our objective was to prove that F inverse of B is closed. This was our objective, which we have put it here. Converse part, I will. So what will be the converse part? So in the converse part, you show that if for a function F, if we choose any closed set in Y and its pre-image is again closed in X, then the function is continuous. Then the function is continuous. And again, to prove the converse part, we will make use of the earlier exercise. Okay. So I will do the converse part as an homework, right? So we to prove the converse part also you need the earlier exercise. You people need the earlier exercise. Okay, the handwriting sometimes I just by the earlier exercise. Okay, so the converse part is left as an homework. So to the converse part, consider the complement of B. Consider the complement of B, which will be open, and use the earlier exercise. And use the earlier exercise. Right? Okay. So this is what continuity is. Okay. So under continuity, pre-image of an open set is open. Pre-image of a closed set is closed. Okay. So I want to do one exercise. So So we will be making use of these two exercises. Okay. So don't think of these two exercises like they are closely related to each other, right? So think of them in a group. So this is one question. Okay. So decide. Okay. So let f is a function from R to R, and f is defined as f of x comma y is equal to cos x squared, cos of squared plus x cubed minus 47y minus some constant times y minus e raised to x minus y squared. Okay, this is a function from R to R. So decide whether the set, so we are given a set of point x comma y in R2 such that cos of x squared plus x cubed plus x cubed minus 47y minus 47y is strictly greater than e raised to x minus y squared. Now this is some subset of R. So decide whether this set is open or closed in R2. Closed in R2. Okay. Read the question carefully. So where does the crux lie? What is the most important thing to answer this question? Okay. Which set we want to discuss for whether it is closed or open? So let me write down the set. So let A is equal to this set. Okay, let A is equal to this set. Okay, so let A is this set. Control C, Control V. Okay. This set is same as the set of points in R2, x comma y in R2, such that cos of x squared plus x cubed minus 47y minus e raised to x minus y squared is greater than 0. This set is same as the set of points x comma y in R2 such that f of x comma y is strictly positive. This set is same as the points of x comma y in R2 such that or what is this set? What is this set? F of xy is strictly positive. What does that mean? What value does f take? If f of xy, if your f is function from R2 to R, right, and f is strictly positive, then what values does your f take? So can I say this is nothing but inverse image of open 0 to infinity under f. So your set A is inverse image of open interval 0 comma infinity under f. Right? Now I want to make one claim. So note that f is a continuous map and open 0 infinity is open in R. So this implies inverse image of an open set is open under a continuous map is open in R2. That is, the set A is open in R2. Now, how to prove the continuity of F? How to prove the continuity of F? This is the question. Should I leave this as an exercise? Prerna?
Yes, sir.
Just make use of the very first definition of continuity. Take a sequence in R2, say xn comma yn, such that xn converges to xn comma yn converges to x comma y, and then prove that f of xn comma yn converges to f of xy. Okay, so I will add that as an homework. Right? I will add that as an homework. So this is your homework. Show that the function you have defined above, show that the function you have defined above is continuous. Okay. So use the very first definition of continuity that you people have come across. This is strange, you know. At few spots, this pen just stop working. Okay, you have to define as above. Okay, I will correct it and then send it to you. Okay, so there is one more exercise that I want to discuss. Where is that exercise? So basically we are done with continuity, but let's discuss a few exercises. I wanted to discuss few different spaces, but okay. So here we are given two matrix spaces x and y and two functions f and g from x to y. So let x and y be matrix spaces. So let 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 me just close and then restart this application. It's working. It's not working properly. Okay, in the meantime, let me take the attendance. 1,
Present, sir.
2, 3, 4,
Present, sir.
5,
Yes, sir.
6, 7,
Yes, sir.
8, 9, 10,
Present, sir.
11, 12, 13,
Present, sir.
14,
Yes, sir.
15, 16,
Present, sir.
17,
Present, sir.
18,
Present, sir.
19, 20,
Present, sir.
21, 22, 23,
Present, sir.
24, 25,
Present, sir.
26,
Yes, sir.
27,
Yes, sir.
28,
Present, sir.
29. Zimad. Okay, Zimad is not there. Still not working. It's strange. Okay, so I will correct it. Okay, it may be because there is the computer is, it is want of plot. So let x and y be matrix spaces. So let x and y be matrix spaces. Let f comma g, let f comma g from x to y be continuous maps, be continuous functions or continuous map. Show that the set E, show that the set E of, show that the set E of the points x in x such that f of x is not equal to gx, f of x is not equal to g of x is open, is open. Okay, so we are given two continuous function f and g from x to y, and our job is to show that this set E where f and g are not equal is open. Okay. Okay, so now let's try to prove this result. So let x belongs to E. What do you want? We want an open set. We want an open set or open ball, right? Open set or open ball U containing x such that this ball is a subset of E. This is what we want, right? So since f of x is not equal to g of x by the Hausdorff property, Hausdorff, Hausdorff's property, there exists open sets. There exist open set. I use taken W and use there be W and Z open sets W and Z such that f of x is in W, f of y is in W Z, and the intersection of W and Z is empty, right? This is what Hausdorff property says. Okay, we have already proved the Hausdorff property for metric spaces, right? What does Hausdorff property says? It says if you have two distinct points, then we can draw two distinct open set around containing these 2 points such that their intersection is empty. This is what Hausdorff property says. So this is your f of x, here is your f of y, and this is your w, and this is your z. Okay. Yeah, this P is quite big. Now, how to proceed next? F is continuous, G is continuous, W is open, Z is open. What does that mean? What about F inverse of W? What about F inverse of Z? So this implies F inverse of W and F inverse of Z are open, right? Because F is continuous, the pre-image of open set is again open. So F inverse of W and F inverse of Z are open in X. They are open in X, right? Hello.
Yes, sir.
So set U is equal to intersection of F inverse of W with F inverse of Z. What can we say about W? What we can say about U? F inverse of W is open. F inverse of Z is open. What about their intersection?
It is also open.
Then U is open. And further, what can we say about that thing? So here is not f of y, g of y here. Okay, here it is g of y, not f of y. What can we say about u? U is open, right? Can I say that u is open and x is in u? Can I say x is in u? So what does that mean? X is in u, it means x belongs to f inverse of w. That is equivalent to saying f of x is in w, which is true. F of x is in w. and x belongs to G inverse of Z, right? So here it is G inverse of Z. My bad. Okay, this is G inverse of Z, right? So x belongs to G inverse of Z. That is equivalent to saying G of x belongs to Z, right? And which is also true. So here it is G inverse of Z. Okay, G inverse of Z. G inverse of Z. Let me redraw this diagram once again. So what is happening is your f of x is here. This is your w, and g of x is here, and this is your z. Right? So u is open and x belongs to u. X belongs to u. Right? What is remaining right now? So we have found an open set U which contains X. The job which is remaining is to show that this U is a subset of E. U is a subset of E. That is the thing which is remaining. Right? So next we show that. Next we show that U. Next we show that it's not working. Next we show that hello.
Yes, sir.
Yes, sir.
Yeah, okay. It had just stopped working. Okay, so let's wait. This is a disaster, technology is disaster. I like that old school teaching style, blackboard and chalks. Okay. Right, so what is remaining is it's not still not working.
सर ड्रॉ पे क्लिक करिए एंड देन पेन पे, फिर वो चल जाएगा.
किस पे, कहाँ पे क्लिक करूँ?
सर ऊपर ड्रॉ लिखा है ना, इंसर्ट एंड ड्रॉ, ऊपर होम इंसर्ट एंड ड्रॉ.
हाँ, ओके ओके, यहाँ पे हाँ.
सर ड्रॉ पे क्लिक करिए, ड्रॉ पे.
ड्रॉ पे क्लिक किया.
तो वहाँ पे पेन्स आ जाएंगे, वो पेन पे किसी पे भी क्लिक कर लीजिएगा.
हाँ, लेकिन ये नहीं वो ठीक है, बट ये काम ही नहीं कर रहा है, फ्रीज हो चुका है पूरे का पूरा एप्लीकेशन. तो देखो मैंने यहाँ पे ड्रॉ पे किया है. Okay, let's now what is remaining is to prove that this U is contained in E. What does that mean? You take any element which belongs to U, then your job is to prove that for such an element, f of x is not equal to g of x. Right? So choose any element, say choose an element y in U, then we want to prove that f of y is not equal to g of y. That is what we want to prove, right? What happens if we go by contradiction? If f of y is equal to g of y, then what will happen? Okay, let me try one more time. It's working. So next, assume that not assume. I don't know why this is not working. So next, let x belongs to take some other element. Okay, not x. So let some other element so next let y belongs to q. What we want? We want to show that y is in E, that is f of y is not equal to g of y. Okay, so on the contrary, assume that y is not in E. So this implies, what does this implies is f of y is equal to g of y, right? Okay. Okay, let's stop here. Okay, this application is not working. So it closed automatically. Hello.
Okay, sir.
Yes, sir.
I will write down the remaining answer and then I will send it to you. It's not working properly. It may, I don't know why. Okay, so let's stop here. This was a mess.